All right, let's have a look at how to name ionic compounds. Now bear in mind, everything in this video is only going to apply to ionic compounds. This video will not include acids or non-ionic, aka molecular compounds. So looking at this, what defines these different compounds as being ionic is their content, which is to say they either contain a metal and a nonmetal, as is the case here and with all the rest of these, aluminum, silver, copper, nickel, cobalt, whatever, these are all metals, or for those that don't contain a metal and a nonmetal, you get this where it contains a polyatomic ion of some kind, or here it's two polyatomic ions. So that is the general rule. These will apply, this naming ionic compounds, these rules apply when either you have a combination of metals and nonmetals or polyatomic ions of some kind are present. So to look at that, let's look at these examples of how you go about naming these, and then after that we'll go through how you would come up with a formula from the name. So to begin with, let's look at this one right here. So we begin with this first formula. Actually, these first three involve aluminum. These involve, okay, silver, copper, whatever. If you're going to name a chemical formula, one thing that's really important is to consider what that name is going to have to look like, in the sense of either you need to have a Roman numeral or you don't. And if you notice, there are various ones here that don't have a Roman numeral and various ones that do. Okay, the big rule is that metals with a variable charge, that could potentially be more than one charge, have a Roman numeral to specify what charge it is, and the ones that are always the same, such as strontium always being a 2+, or magnesium is always a 2+, or that are just not metals at all, as in these are both polyatomic ions. These things, because their charge is reliable, dependable, and constant, it is always going to be a no Roman numeral sort of situation with their name. So we look at that, and I can already say, no Roman numeral needed for these. Yes, I need a Roman numeral for these. Yes, I need a Roman numeral, and then for these, no Roman numeral, because, how do I know that? No Roman numeral, because these have a constant charge. I'll even make a note of that. With no Roman numeral, constant charge. All right, now, that being said, if there's no Roman numeral, naming is very easy. That is aluminum, that is sulfate. The name is aluminum sulfate. It doesn't how many there are, or it doesn't matter how many there are. This is a mistake and a typo. That's the correct formula. Regardless, it's aluminum, it is sulfite, aluminum sulfite. This is aluminum hydrogen sulfite. This is silver, this is oxalate, silver oxalate. Silver and zinc are the two transition metals that always have a dependable charge, therefore they never need a Roman numeral in their name. Now, copper, on the other hand, does need a Roman numeral, so we're going to say that we need to determine what the charge of copper is, so that we put that for the Roman numeral. Oxygen, being a charge of -2, we'll notice that there are two of them, giving a total of -4 charge. The copper must therefore balance that by being a +4. We will therefore call this copper with a Roman numeral 4 oxide. Copper 4 oxide. Do not make the mistake that some people make, which is they'll write copper, put a Roman numeral, and then oxide. And they'll take this and they'll want to say, oh, it's copper 2 because there's a 2 in the formula. And don't do that. That is wrong. There, emphasize that. Now, as for the next one, nickel and sulfate, but because nickel is a transition metal with variable charge. We're going to have to figure out what it is. Sulfate's a -2, and there's one of them. So -2 must be balanced by a +2. Therefore, we're going to call it nickel 2 sulfate. Here, cobalt, dichromate. Again, dichromate's a -2. Cobalt must therefore be a +2. Cobalt 2 dichromate. Simple as that. Now here, ammonium and a bromide ion. Well, ammonium's always a +1, no Roman numeral needed, so we simply put ammonium bromide. Here, ammonium nitrate. And here, this is ammonium once again. This is a sulfite. So it is named simply by what it is, ammonium sulfite. There it is. All right, so that's a quick overview of how you come up with a name from the formula. Let's see how you would use the name to come up with a formula. In other words, go the other way around. This is in many ways quite simple. It's just a matter of keeping a track of what you're doing and being systematic about it. Now, let's start here, iron 3 oxide. We'll say that means iron with a 3+ charge. Iron 3 means iron with 3+ charge. Oxide means oxygen ion, which if you check the periodic table, you'll see has a charge of -2. So we switch the numbers around. That means we're going to have 2 irons and 3 oxygens for a final formula of Fe2O3. Manganese 4 perchlorate. Manganese is Mn. Here it's specified as having a +4 charge, and perchlorate is ClO4 with a 1- charge. So we do as before. There's going to be 1 manganese, and there's going to be 4 perchlorates. So our final formula is going to be manganese with 4 perchlorates, and that's how we write it. The parentheses is necessary. Without the parentheses, it would be 1 chlorine and 44 oxygens. The parentheses is critical to show that you have 4 of this entire thing. Now, let's look at this one next to bring up actually something that I have in mind to mention. Cobalt carbonate. Okay, cobalt 2 carbonate. It's cobalt with a 2+ charge. Carbonate is CO3 with a 2- charge. First of all, I can tell you just need 1 of each in the formula because they're equal and opposite charges. Final formula is going to be 1 of these plus 1 of these. But supposing that wasn't obvious, you can cross the numbers. You can do the crisscross method. So that's 2 cobalts and 2 carbonates, CO2, and then 2 carbonates, oops, CO3 and 2 of them. And then you simplify that to 1 cobalt and 1 carbonate. Now, of course, the fact that cobalt's a 2+ and carbonate's a 2-, they're equal and opposite charge, so you just need 1 of each. But if you want to do the crossing of the charges, the crisscross method, this is how you'd go about it. Because, hey, after all, if you had calcium and oxygen and you wanted to combine them, you'd go through the same process of calcium to O2 becomes calcium, it becomes 1 of each. A 2-to-2 ratio is the same as 1-to-1. Likewise, a 2-to-2 ratio is the same as 1-to-1. And because there's just 1 carbonate in this formula, no parentheses needed. This is the final answer. Just as this was the final answer for the question before. So if there's more than 1, you need a parentheses. If there's more than 1 polyatomic ion, if there's only 1 polyatomic ion, no parentheses needed. And of course, if it's not a polyatomic ion, there is no polyatomic ion for O3, at least that we're going to be seeing here. No parentheses needed either, only in the case of having a polyatomic ion and more than 1 of them. So let's look at the rest of these. Yes, the number 1 may not belong in a formula, but it certainly can belong in a name. So cobalt 1 carbonate is cobalt with a +1 charge and carbonate, which is CO3 and a 2- charge. That tells me it's going to be 2 cobalts and 1 carbonate. So cobalt, there's 2 of them. There's your carbonate. Again, there's only 1 carbonate, therefore no parentheses needed. Strontium carbonate. Notice, no Roman numeral because strontium's always a +2. Yes, strontium, 2+, carbonate, CO3, 2-. They're equal and opposite charge, so that means I just need 1 of each. If you were to switch the charges, you'd follow the same process as here. You'd get strontium, carbonate, looking like that. Now magnesium oxide, we'll go through the same process there, where you put the 2 down here and the 2 down here. So you start with 2 magnesiums and 2 oxygens, and then you simplify. A 2-to-2 ratio is the same as 1-to-1. And that is your formula for magnesium oxide. And then let's see, ammonium phosphate. Ammonium is NH4, phosphate is PO4, 1+ charge on the ammonium, 3- charge on the phosphate. That tells me I need 1 phosphate for the formula and 3 ammoniums. So that means the final formula is going to be involving NH4 and 3 of them as decided here, and 1 phosphate. Let's box that up to show that that's the final answer. And all right, that's a quick overview of how you come up with a formula given the name for an ionic compound or the name given the formula of an ionic compound. Remember that these rules only apply to ionic compounds, so should you see anything that has an H at the beginning, that's an acid. These rules don't apply for that. Should you see anything that is all nonmetals, that is a molecular compound, and these rules don't apply to that either. So all right, there we go, ladies and gentlemen. Happy studies.